Hello and welcome to the 24th lecture. So today we're going to go over some questions from the practice exam and hopefully clarify or bring back to the forefront of your mind some of these things that we've been learning over the last 4 or so weeks since the last midterm. So there are many questions. We're not going to do all of them. I'm going to do the ones that seem to me to be the trickiest ones, the ones that you might have the most difficulty with. So here's the first one. I think this is question 2. So we have a cube. A cube is decreasing at a rate of 2 centimeters per second. At what rate is the volume of the cube changing when the volume is 125 centimeters cubed. Okay, so this is a related rates question. It's a topic we talked about a fair bit. It's something I particularly like to talk about. So let's work through it. So how do we start? We have this stuff in the language of words, and our first thing is we're going to draw a diagram to kind of clarify what is going on for us. So we have a cube. Like this, and we're going to second, going to try and identify what are the quantities in this bunch of words. And what we have of a cube decreasing at a rate of, well, this actually makes no sense. I think it should be the cube's side length should be decreasing. So each side of the cube has sides decreasing at a rate of 2 centimeters per second. So one of the quantities clearly is the sides, right? At what rate is the volume decreasing? At what rate is the volume of the cube decreasing or changing when the volume is 125 cubic meters? So our quantities are the sides and the volume. So these are the ones we can read off straight away. So I'm going to introduce some notation for these things, and we're going to have to decide what they depend on. And because it's telling us that the sides are decreasing at a rate of 2 centimeters per second, clearly everything is described in terms of time, right? So we're going to write R of t for the sides, and I'm going to let V of t be the volume, because that's the quantities inside this story here. All right. Now we're going to rephrase the information in the language of math. So info. What information do we have? Let's underline the part that's the information. The cube has got sides decreasing at a rate of 2 centimeters per second. So it's a cube, so all the sides should be side length, I guess, has sides whose length is decreasing at 2 centimeters per second. So we express that R prime of t is equal to -2, right? because that's what we know. The side lengths are decreasing at 2 centimeters per second. The side length is given by r of t. Expressed in the language of maths, it's simply this, right? Very concisely expressed by this. That's the information. Now I'm going to rephrase the question. The question is, at what rate is the volume of the cube changing when the volume is 125? Okay, let's underline this. This is the question. Okay, now, in the language of maths, what is this? At what rate is the volume of the cube changing? Well, volume we've denoted as v of t. The rate of change of v of t is v prime of t. So this is a question about v prime of t. So it's saying, what is v prime of t when the volume v of t is 125 cubic centimeters? So this question is, what is v prime of t when v of t is 125? This part right here is literally the language course, the language component part of this course, where we're just translating from the language of words to the language of maths. And we've done that. We've done a perfect translation, and we have this very neat, concise way of expressing all that stuff up here. Okay, cool. So having the information and having the question, we now know that the only way we can possibly answer the question with the information if there's some kind of relationship between the stuff of the information and the stuff of the question, right? And we have the picture to help us here. And the stuff of the information is about r, right? And the stuff of the question is about v. So we're hoping there's a relationship between v and r, and sure enough, we see that there is one, right? Because what is the volume of the cube? It's going to be the base times the height, right? So v of t, the base of the cube, is just going to be r squared. The height is r, so v of t is going to be r of t to the power 3. So, relationship. Write it again. V of t equals r of t. So my v's and my r's look a bit similar. Let me correct that. V of t equals r of t to the power 3. And then, since our question is about v prime, and our information is about r prime, the natural thing is to differentiate this thing. So, if the equation, and we're going to get v prime of t equals 3 r of t squared r prime of t. And we can start to put in information. So we know that r prime is always equal to minus 2 every time. So it's going to be minus 6 r of t squared. Yep. And the question we asked is about the specific time when v of t is 125. So the thing that we are looking for is v prime of t at this specific time. You write this v even more like a v. No? And what we don't know is what r of t is at this moment when v of t is 125. But we have this relationship here, also put here, so we can figure it out. So we need to know r of t when v of t is 125. And that's not hard because we just have this. So from star we have that r of t at this moment when the volume is 125 is going to be the third root of 125. Okay, so what is the third root of 125? What's the third root of 125? It's just going to be 5, right? Because with 5 times 5 is 25, and then times 5 again, it's 125. So this is just 5. Cool. So we now know that r of t is just 5 at this instant of time that we're interested in. We can just plug directly 5 into this, right? So v prime of t is going to be equal to minus 6 times 5 squared, which is 25. And what's that going to be? It's like minus 150, right? So 5 times 25 will be 125, so I think it's minus 150. So the volume is decreasing by minus 150 cubic centimeters per second when this happens. Okay, that seems to be our answer. Let's check. Yeah, looks good. All right, let's do another one. Question 7. Okay, so we have a bunch of statements, and we have to figure out which one is correct. So the first statement is that f of 1 equals 1 and f of 3 is equal to 5. And then it says, is there a number such that f prime of c is equal to 2? So is there c in the interval 1, 3 such that f prime of c is equal to 2? Okay, so let's visualize the situation. So I have a function, and at 1 we are at 1, and at 3 we are at 5. And the question is there some c such that f prime of c equals 2? Well, whatever the function's doing, it's going like this, going through these 2 points, right? And if we connect up these points with a straight line, what do we see? This straight line, the secant line connecting 1, 1 to 3, 5, we are going along by 2 and we're going up by 4. So the slope of the secant line is exactly 2. So slope 2. Yeah, and what we're looking at is exactly the situation of the mean value theorem, but you don't even have to remember it. At this point, you can just look at this diagram and ask yourself, do I believe that there exists some c such that f prime of c equals 2? Well, if f prime of c equals 2, then that means that the tangent line we take at the point c, f of c, will be the same slope as this blue line, and for sure that's got to be the case, right? For example, here and here. So yeah, that's true. So true by the mean value theorem. Okay, let's do question 2. Or statement 2. So in this case we have f of 1 is equal to 1, f prime of x is less than or equal to minus 2 for 1 between x and between 3, and then it says then f of minus 3 is Oh, I'm sorry. I'm accidentally doing statement 3, but okay, let's continue it. Let's do statement 3. And it says f prime of 3 is less than minus 3. Again, we visualize it. So let's create this situation. So we have, again, 1 is 1. We have the derivative is always less than or equal to minus 2. Yeah? And then it says, then f of 3 is less than minus 3. So here's 1, here's 2, and here's 3. Yeah? So we are going down, okay, with a slope, and the slope is always less than minus 2. Okay, so let us think about how far, or what's the least amount of going down we could possibly have, so that what's the least amount down we can be at 3. So since we're going down with a rate of minus 2, that means that every time we go 1 along, we'll go down by minus 2, right? So here we are starting off at 1, 1, and then as we go along by 1, the most we can we can be going down by just minus 2. We might be going down by more, but the only restriction is that this thing is less than or equal to minus 2. Yeah, so we could, if we are decreasing with the minimum amount possible given by these hypotheses, we could be just going down by minus 2 as we go from 1 to 2, which would put us down here at minus 1. Yeah? And then we do it again. We go from 2 to 3, and the very least amount we can end up going down is again down by another minus 2, yeah? Which would indeed put us underneath minus 3. Yeah? And if we try and express that a little bit more precisely, what are we actually saying? Well, what is the least, given this hypothesis, what's the function that's going to go down with the least amount of slope? It'll just be the one whose gradient is got slope exactly minus 2 all the time. So it'll just be the linear function going down with slope minus 2. So if we have a linear function going down with slope minus 2 like this, then this is a function which satisfies our hypothesis. Our actual function has to be going down with possibly a steeper slope, so it has to be underneath this thing. Yeah? But this guy is as high as it can possibly be at 3, because this is the least way we can actually have this being true. Yeah? And we just carefully see how far this can go down. So from 1 to 2, this can go from 1 down to minus 1, and then from 2 to 3, it goes from minus 1 down to minus 3. So this will indeed be, let's keep the color consistent, 3 minus 3. So just based on that kind of reasoning, we expect this to be true. Yeah. So when I talked about this in class, another metaphor, not really a metaphor, it's almost like a direct rephrasing of the situation, is to think about this in terms of velocity. So if you're at position 1 and you have velocity less than minus 2, so you are going more fast in the backwards direction than minus 2, or the slowest you can be going in the backwards direction is exactly minus 2. And it's asking how far back you can be. Are you at least back position minus 3 from where you start? Well, the very least far back you can be is if you're going at the least backwards speed direction you can be going, which is minus 2. So you start at position 1, going steadily back at velocity minus 2. After whatever unit of time, let's say hour, after 1 hour you go from 1 to minus 1, and after 2 hours you go from minus 1 to minus 3. Yeah? And you are indeed at least back position minus 3 from 0. So this would be true. Okay, but this thing is asking us to use the mean value theorem. So we already think we know the answer just from these elementary kind of drawing the picture, just reasoning it out, just applying common sense. But let's use the mean value theorem tool that we know about. So what does the mean value theorem say? So by the mean value theorem, there exists some C such that f prime of C is equal to f of minus 3 minus f of 1, but f of 1 is 1. Let me put it in directly over not f of minus 3, f of 3 over how far we've traveled. And we've traveled from 1 to 3, which is 2, right? And we also know that this thing is always less than or equal to minus 2. So let's put it like this, minus 2. And now we unwrap this stuff here. So this implies, let's multiply by 2 on both sides, and then let's add 1. Well, let's do it step by step. So minus 2 is bigger than or equal to f of 3 minus 1, and that implies that minus 3 is less than or equal to f of 3, and so it's true. Okay, good. So we're absolutely certain it's true. We've confirmed it with two well, actually, these reasonings are very similar, but we've confirmed it in two different ways. Right? All right, so that is statement 3. Let us do now statement 2 that I accidentally skipped. So statement 2, we have f of 1 is equal to 1, and f prime of 4 is bigger than or equal to 4 for 1 less than equal to x less than equal to 3, then f of 3 is bigger than or equal to 10. Okay, same thing. I want to first see if I believe this from just drawing the picture and thinking about this in an elementary way, and then we're going to use mean value theorem to repurpose this graph. Okay, so we have f of 1 is 1. We have that the derivative is always bigger than or equal to 4, so the very least amount it can possibly be going upwards is if we actually have a linear function whose slope is 4, right? So if we had a linear function whose slope is 4, then going from 1 to 2 would be going up by 4, so we'd end up here at 5, right? And then going from 2 to 3, again, the very least we can go up is 4, so we end up here at 9. So this thing here would be the coordinates 3, 9. Right? And that's a nice function that satisfies exactly our hypothesis, right? It's got slope 4, right? I mean, we can explain, if you're in any doubt about it, just use the language of math to further clarify the situation, right? So we can just describe a function that does this, a function that has slope 4, and that goes through 1, 1, just by the stuff we know. So for example, and this is how we create a tangent line. If we let f of x be 4 of x minus 1 plus 1, then that thing has slope 4, and it goes through the point 1, 1, right? And what is that? That is 4x minus 4 plus 1, so we have minus 3, right? And it satisfies exactly what we need. So f of 1 is just 4 minus 3, which is 1. The derivative is 4, so that's always true. And then what can we have here? If we have f of 3, then we have 4 times 3, which is 12, and then minus 3, which is 9. And that's what we know already from the pictures. So this is not true. We just have an example of a function that satisfies our hypothesis for which the conclusion is false. So this is false. And note that we found this by first drawing the pictures and not trying to just mess around with mean value theorem straight away, which is the thing I'm trying to sell to you. Don't start to apply some kind of tool, some kind of algorithm until you have drawn the pictures and you have some idea what you're doing, what the thing means, and what the answer is. And often just from drawing the pictures, just from visualizing and applying common sense, use the reformulation in terms of position and velocity, you will easily come to the answer and then nail it down by using mean value theorem. Okay, but in this case, we know it's false. We have an explicit example. There's no doubt about it. We are all set for this particular statement. We have a final statement. Okay, let me squeeze it in. It's not too hard. Yeah. Okay, it's hard to squeeze it in. So the final statement is that, so this is 4, that f of 1 is the same as f of 3, which is equal to 1. And then the statement is that the graph of f has a horizontal tangent somewhere between 1 and 3. And for sure we know that's true. Let's just squeeze in some picture here. So this is my hypothesis here. So at 1 we're at 1, and at 3 we're at 1. So whatever the function has to do, has to be something like this, right? And it's asking that, so this is the question. It's asking, does there exist C such that, no, it just says that there's a horizontal tangent line somewhere in the interval, which is the same, as you know, as just saying that there exists some C between 1 and 3. That is the statement of 4. And yeah, for sure that's true. We just see it. That's just Raleigh's theorem is a special case of mean value theorem, and we can just see it from the picture. It's definitely the case. So that's true. And there we go. That does question 7 for us. Okay, and raise the board, and then we'll do some more. Okay, question 18. So we have this function here. And we asked all this stuff, basically asked to sketch. We're going to find intervals increase, decrease, local maxes, local mins, intervals of concave up, concave down, and points of inflection. So everything. So sketch. Okay, solution. So, as always, we're going to start with 0th order information. So information that we can get without actually having to take the derivative. And let's put some stuff up. Let's block in some 0th order, rough order features. So we know for very large x, this is like x to the 4, right? Because these numbers -1 and -3 don't matter for huge x. So it's way out here, it's positive, climbing like this. We know it is 0 at 1 and it's 0 at 3. So here's 1. Let's make this thing be 3, and it is 0 on these things. Maybe I want to put 3 a little bit along to make a nicer diagram. So let's put 3 over here. Okay, and it is growing out like this. All right, so it's 0 here. When x is actually equal to 0, then we're going to have minus 1 times minus 3 to the power 3. Minus 3 to the 3 should be 27, or minus 27. So we're going to have minus 27 times minus 1, so it's actually crossing around here. It's not to scale, but it should be crossing around here. It's coming in something like this. It's crossing here, and it's crossing here, and then somehow it's going up again. Okay. These are our rough features. Okay, so now let's take first order. Can't spell order. Which we are going to get by differentiating, of course. So it's just the product rule. Differentiate the first guy, leave the second guy alone. Leave the first guy alone. Differentiate the second guy. Factor out stuff so we can see what we're doing. Let's factor out just x to the x minus 3 squared. And we're going to have x minus 3 minus 3 of x minus 1. And what's that? X minus 3 squared. And that is, let me check, I didn't get this wrong. Yeah, I don't think it's a minus, right? So we factor out this x minus 3 squared. So we're just going to have x minus 3 here. And this is not a minus, it's a plus. It's like this. Okay, so then we're going to have 4x. And then we have minus 3 again. So it's 4x minus 6 right here. And let's take out just a factor of 2. So we have 2x minus 3 squared, 2x minus 3, and that's it. All right, cool. So what does that tell us? It tells us the derivative is 0 at 3 and at 3 over 2. Okay, so the derivative is 0 at 3 and at 3 over 2, so somehow flattening out around here. Okay, and then this thing looks like it's most likely going to be, so 3 over 2 is somewhere between 1 and 3. It looks like it's going to be, we have a local minimum. But we're going to know for sure because we are now going to find the intervals of increase and decrease. So intervals of increase and decrease. And then we create a table. And then we put the stuff. So what is our first interval? Our first interval is going to be from minus infinity to 3 over 2. And then our next interval will be from 3 over 2 to 3. And then our next interval will be from 3 to infinity. Right? And let's put in our factors. Actually, we are making too much heavy lifting here. This is always a positive number. So I actually don't care about this guy very much. I mean, okay, since we've started, let's put it in just to be systematic. So if we have x minus 3 squared, and then let's put in this 2x minus 3. Okay, so this thing is always positive, right? And then the sign, I mean, this is our derivative right here. The sign will be determined just by the factor here. So if we have a number which is less than 3 over 2, okay, and then we subtract 3, we're going to have a negative number, right, for sure. So this is, start again. If we have a number which is less than 3 over 2, we multiply by 2 and subtract 3, and for sure it's negative. If it is bigger than 3 over 2, when you multiply by 2 and subtract 3, then it's going to be positive, and also positive here. So we have negative, positive, positive. All right, let's see if that makes sense with what we have. Yeah, so negative slope, we're going down, 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 down till we get this here, which is 3 over 2. So it's going to be around here. This is 3 over 2. So the gradient will be going down, 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 like this. I'm going to have a local min here, and then it's going to go up, and it flattens out. And then my guess is, it has to go up again, right? It has to go up again. You know? So that is the first order information. So if we look at 3 over 2, we have, this is where we have the change in sign. We go from negative to positive, negative to positive. So it's a local min at x is equal to 3 over 2. So at x is equal to 3 over 2, local min. And that's the only local min we have. The actual value of the local min is what happens when we stick in 3 over 2 into this function. And I don't want to do the calculation. So the local min is f of 3 over 2, whatever that is. All right. Yeah, that does make sense. It will be at least a negative number because this part will be positive and this part will be negative to a power 3. So at least it's here. All right, good. So that's our local min. It's this value here. This is f of 3 over 2. And now we're going to do intervals of, we're going to do second order information and do intervals of concave up and concave down. So second order info. And we differentiate again, right? So this is our expression. So we differentiate the first guy, leave the second guy alone. We're going to have 4x minus 3, and then 2x minus 3. And now leave the first guy alone, 2x minus 3 squared, and then differentiate the second guy. We just get another 2, so times 2. Let's clean that up. Put it over here. And let us factor out a 2x minus 3. And that's going to give us 2 of 2x minus 3 from this thing. And we are going to have just another 2 times x minus 3 from this thing when we pull out 1, 2x minus 3. And then let's clean that thing up. 2x minus 3. We're going to have 4x plus 2x, so it should be 6x. And then we're going to have minus 6 and then minus 6. Right? That's minus 12. Let's factor out a 6. So we have 12 of x minus 3 and then x minus 2. And that is our second derivative. Now we do have these non-trivial factors that will change sign. So we're going to create a table and check out what happens. So our first interval, right, is going to be from minus infinity to 2. Because as we talked about it when we discussed this stuff, the second derivative cannot change sign from minus infinity to 2, because if it did, there would be another point where the second derivative is 0, and there isn't. The first one where it's 0 is at 2. So second derivative is either positive or negative on this interval, and we're going to figure out which one. Next interval is this. Next interval is this. And then we put in the factors. So x minus 3, x minus 2, and then the second derivative. And then put stuff in. So this shows negative, again negative, so positive. This for sure is negative, and now here it's positive, so positive. So, not positive, negative, sorry. This for sure is positive, and again positive, so positive. Okay, so we have that it is concave up all the way to 2, and then from 2 to 3 it's concave down, and then 3 onwards it's concave up. Okay, I think that indeed can fit. So let's see. So it is concave up all the way to 2. So 2 is here. So we can indeed create a function that's concave up. So indeed that's minus 27 is much higher than this. So this is, sorry, 27 is much higher than this. So this is 27, and we are concave up going down, 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 crossing, concave up all the way to 2. I'll put in the tangent lines in a second. And then from 2 until 3, we are concave down. That makes sense too. We can curl down like this. And then from 3 onwards, so this is 3, we are concave up again, and yeah, we can do that too. Concave up like this. Okay. And you remember what concave up means? It's like this. So we're curling upwards above our tangents, right? Concave up, right? So on this part of the graph, from minus infinity up to 2, we should be able to fit the tangents underneath it. And yes, not that way. Yes, we can. Yeah, and then from 2 to 3, it's concave down, so it's underneath the tangents, and then from 3 onwards, it is again concave up. It's above the tangents, and all those things fit together. Cool, so we can do this stuff. The only tricky thing is getting these little algebraic calculations correct. But the good thing is, well, the saving grace of this kind of stuff is that if you do get them horribly wrong, then you can't fit together the information. So once you can put in all the information and it's consistent and it's such and it does all fit together, then you can be somewhat reassured you haven't made an algebraic mistake. Of course, in the midterm, I don't want you to leave until you've checked everything, used all your time. It's an inefficient use of your time to leave the midterm early. Please spend your whole time checking over your answers. Okay, that is question 18. Question 11. So we have a picture right here. This is -1, this is 1, and the picture does something like this. Goes down to -2, goes up, hits 1, goes down again, like this. So -2. And it says this is the graph of the first derivative of f, so important to identify what it's the graph of. So graph of the first derivative, so graph of f prime. And then we have a bunch of questions about, or a bunch of statements, and we have to see if we believe they're true or not. So first statement, I, f is decreasing on -1 to infinity. Let's see if we believe that. Okay, so we know that if the derivative is negative, we have a negative slope of our function, it is decreasing, right? And we see that the derivative is negative. Indeed, it is always negative every point from -1 to infinity except at this point 1 where it's actually 0. However, that doesn't mess things up for us because if we take any 2 points from -1 to infinity, it's still going to be the case that we're going to be decreasing when we consider these 2 points. So let me express that in the language of math. It's better done that way. So this is the question mark. So given any, say, a and b in this interval -1 to infinity with a less than b, we want to have that if it's decreasing, then f of b is going to be less than f of a. So that's a mathematical reformulation of the statement, is it decreasing? And for sure that's true because we know it is a theorem from -1 to 1 itself, because the derivative is strictly negative there, and it's true from 1 to infinity. Our only doubt about this stuff is this one point where the derivative is 0. However, that doesn't mess things up for us, because if we have, for example, a is here and b is here, then this statement that b is less than a is still clearly got to be true. And let's reformulate this in terms of velocity. So this is the graph of a velocity, okay? And the velocity is always negative. So at time a, we have a negative velocity like this, right? We're moving in time from time a to time b, right? And if we have negative velocity all throughout this time period except at time 1 where we've stopped, so we're moving backwards, and at time 1 we're stopping, but then we continue moving backwards, yeah? Then it's still definitely the case that f of b is going to be less than f of a, yeah? So the fact that we have some point here where we've actually just stopped for a second isn't going to prevent this from being the case. So the kind of putting the graph like this where it touches the x-axis at one point to try and throw you off a little bit, but don't be thrown off. It's definitely got to be the case that f of b is less than f of a, and it doesn't matter how close we put f of b to 1 or f of a to 1, because no matter what, even if a was right here, just a tiny bit to the left of 1, and b was a little bit to the right, still means that as we go from a to b, we're moving backwards a little bit, then we stop, and we're moving backwards a little bit more. And for sure, therefore, f of b is behind f of a, going that direction. In other words, f of b is less than f of a. So this is true. So true. Okay. F has the local minimums. Let me write the statement. F has a local min at x equals -1 and x equals 1. Okay. So if we look at x is -1, what's happening with the gradient? The gradient is going from being positive to negative, right? Positive to negative, yeah? So what happens if we have something which goes from, does it definitely say local min? Sorry, local max. Local max. So what happens if we have a gradient that goes from positive to negative? Take your hand, positive to negative, right? If we go positive to negative, then we do indeed have a local max. So here, yeah, there will be a local max. But they're trying to trick us here, because here, if we look at this, then in our heads is that we're looking for a local max, and we see this shape, and it's a local max as well, and we go, okay, that's another one. But no, that's not what we have. This is not the graph of f, it's the graph of f prime. Yeah? And here, around 1, we are not having a local max because, again, it's the graph of f prime. This is the point where we are going backwards with velocity and we stop at 1 and then we continue to go backwards, right? So there is no local max here. The sign of the derivative will be negative and then negative again, right? So as we go from something less than 1 to something bigger than 1, what happens? We're going down, we flatten out, we go down again, yeah? Down, flatten out, down again. So it's definitely not a local max, right? It's not a local min, it's not anything here at 1. But it's really easy to make that mistake when you're in a hurry and you look at this shape and you have the words local max in your head. So this is a typically tricky kind of question trying to test how well you're visualizing and thinking about what these things mean. It's actually a very good question. It's actually the kind of question that's going to distinguish students who learn carefully the meaning of this language as opposed to those who try and memorize steps to answer questions. So all of you hopefully are doing the former rather than the latter, and you're thinking about the meaning and you're not going to get trapped. Take this as a kind of warning of how these questions can be set up to trick you. Because this is an easy mistake to make, but it's not a mistake if you force yourself to think about the meaning of the stuff you're doing all the time. You know? So the answer is no. So false. Not a local max. Add 1. Okay, next statement. F is concave up. Let's put it over here. F is C up on minus infinity to 0. Okay, let's think about what C up is. C up is concave up, right? Concave up is like this, right? We are curling like this. We are above our tangents, right? If we take your hand and do a concave up curve, what do you see happening? You see that the gradient is increasing, right? The gradient is increasing, yeah? And also know that the second derivative is positive when it's concave up. But hopefully you know the second derivative is positive because you're doing this with your hand and you see that the gradient is increasing when it's concave up, and therefore the second derivative is positive, right? So f is concave up on minus infinity to 0. That would be the case if and only if the gradient is steadily increasing from minus infinity to 0. And let's look. This is a picture of the gradient, right? As we go from minus infinity to 0, is it steadily increasing? No, it's absolutely not. The gradient is actually decreasing as we go from minus infinity to 0. So it's absolutely not concave up on this, so false. Okay. Fourth statement, f has inflection points at 0 and at 1. Point of inflection is p of I at 0 and 1. Okay, point of inflection, I should write that more expressly, at x equals 0, x equals 1. Okay, points of inflection are points where we flip from being concave up to concave down, or concave down to concave up, right? We have a picture over there of the gradient, right? And we're going to think about what that means in terms of the gradient. So we've just recaptured or recalled for ourselves that when it's concave up, the gradient is increasing. When it's concave down, the gradient is decreasing. Yeah? So this would only be true if at 0 we would go from the gradient being increasing to decreasing, or vice versa. Let's look what happens at 0. Yeah, the gradient is going from being decreasing to increasing, decreasing to increasing. So yeah, it's definitely true at 0. And let's look at x equals 1. yeah, it's also true. The gradient is going from increasing to decreasing, increasing to decreasing. So both of these things are true. True. So the actual answer is that I and IV are true. So I and IV are true. Okay. All right, we have a log differentiation question. Let's just squeeze one in. Question 17. And we want to find dy by dx of y of x equals x to the sine of x. Okay, so this is the procedure when we have some very difficult looking differentiation. Don't panic. Think of the most powerful tool you have for differentiation, and that is log differentiation, what I call the hammer, right? When you have something really difficult to differentiate, don't panic, think of the hammer. And this thing can be crushed by the hammer. And what's the hammer? We just apply log to this thing and we take the derivative of log, because when we differentiate log of a function, we know by the chain rule it is just y prime of x over y of x, right? So then we can find what y prime is by multiplying through by y of x. So apply log. So log of y of x. This thing comes down. We're going to have x sine of x log of x. And then this is a perfectly easy, well, this is a reasonably straightforward thing to differentiate because it's just a product of stuff we know, right? So we differentiate and we have y prime over y again, because that's what derivative of log is. And we differentiate each of these terms. Differentiate the first thing, leave everything else alone. Sine of x, x. Leave the first thing alone, differentiate the second term. We're going to have x cosine of x log x. Finally, x sine of x, and then differentiate this thing, and derivative of log is 1 over x, so we just get this. So then y prime is what we get when we multiply the y of x through. The y of x is given by this, so it's going to be x times x sine of x, and then everything we have here. Sine of x log x plus x cosine of x log x plus sine of x, and that's it. Cool. And there's another one out, there's b, but it's the same. It's a difficult looking differentiation. We apply the hammer, we take logs, we differentiate, we multiply through by y of x. This tool makes hard differentiation become easy. And if you've learned it, if you've practiced it, you won't have difficulty with these kind of questions. So this should be a relatively straightforward one. The main thing that happens is that people panic and they look at this and they think, okay, when they apply, to try and do some kind of weird power law to this. This is nothing you can apply the power law to. This is not x to some power, this is x to some function. And as I talked about even in the last class, whenever we see that, we think, okay, we're going to take log because we don't want to deal with some function to the power of another function, but taking log just turns into the product of things, and then we're all set. Okay, cool. So that one's not too bad. Let's do a few more. Okay, question 20. Okay, the tangent line to y of x which is equal to, well, just the function y of x at 1, 2 is parallel to this thing. And then it says given h of x, which is f of x squared, find h prime of 1 and k prime of 1. Okay. All right, so let's put some pictures in play to describe this information. So we have a function y of x, and we are interested in this tangent line at 1, 2. So this is 1, 2, it's some kind of function like this, whatever it is. Let's not make it so weird. Whatever it is, something like this. And what do we know? We know that that its tangent line is parallel to some specific line, which is given by this thing. So let's write this, let's figure out what this line looks like. So let's figure out what this is. So let's solve for y, and if we do that, we have that 2y is equal to 4x minus 1. Let's divide through, we have y is equal to 2x minus 1 over 2. And the only thing we want from this is the slope, because it says the t-line is parallel to this line, right, which only gives information about the slope. And the slope of this thing is 2. So we know, therefore, that the slope of the t-line has to be 2. So from this thing, so from this sentence, from the, let's make something that makes coherent sense, from the underlined sentence, we know the slope of the tangent line of the function at this point 1, 2. This is the point, right? But we also know that the slope of the tangent line at 1, 2 is given by the derivative of the function at 1. Sorry, this is the x coordinate. Yeah. So that means that we know that f prime of 1 therefore has to equal 2. That's what we can deduce from this underlined sentence up here. Yeah, that has to be the case, because this guy is whatever at some line like this, okay? And so that's the line by this thing. And we know that the tangent line is parallel to this. So if we drew the tangent line, it's going to be parallel. And the slope of the tangent line, again, is given by the derivative of the function at 1. And therefore, we know that f prime of 1 is equal to 2. Cool. So that is the way they kind of wrapped it up. That's the clue for us to kind of unravel, which again is not hard if we are drawing the pictures and we know what these things mean. And then it says find h prime of 1 and k prime of 1. And we just differentiate to see what h prime of 1 is, or h prime of x is. We apply the chain rule, and let's differentiate the k Again, we apply the chain rule. And then we just put in stuff, right? So h prime of 1, put in stuff. F prime of 1 is exactly what we learned already, that's 2. And then times 2 again, it's just 4. And then k prime of 1, that's 2 times f of 1. F of 1 is given to us, it's equal to 2, because we know that this thing has got a tangent line at 1, 2. And the only way it has a tangent line at 1, 2 is if it goes through the point 1, 2, right? So we know that f of 1 is equal to 2. You just see it from the picture, you know? So, where was I? Here we are. K prime of 1 is 2 times f of 1, which we know is 2, times f prime of 1, which again we know it's 2. Yeah, so 2 times 2 times 2, which is 8, so it's 8, and that's it. So if we draw the picture, if we visualize what this thing is giving to us in terms of information, this is computationally very easy to do, you know? And hopefully you people won't get stuck with this. And if you did get stuck with this, it's again because the information we're given is somewhat encoded in a different way, but we just draw the picture that represents it, we think about it, and we have exactly what we need. Cool, let's do a final one. Okay, question 22. So given f of x, which is equal to e to the minus x squared, then it's asking us for all the standard stuff, increasing, decreasing, local max, local min, concave up, concave down, so basically sketch this thing. Okay, so solution. Again, we do the 0th order information first. The information we get without taking a derivative. As we let x tend toward either positive infinity or negative infinity, it's flattening out for sure, right? So it's flattening out like this. It's symmetrical because it doesn't notice we have x or minus x. At 0, it is just e to the 0, which is 1. It's 1 like this, so it's kind of doing some shape like this. You know? Okay, cool. That's, I think, the only 0th information we can get from this. And now we have to differentiate to get more. So first order, so solution 0th order. And now the first order. And we differentiate. So apply the chain rule. Differentiate the outer function, we just get the same thing. Differentiate the inner function, we have minus 2x. So this is just equal to minus, okay. And I forgot to put the x here. All right, so that's cool because that's an easy thing to understand. We don't have to create a table. This is only 0 when x equals 0, so f prime of x equals 0 only when x equals 0. And if x is positive, then the sign of this is negative, and if it's negative, the sign is positive, which is consistent with what we see here. So we have the intervals of increase and decrease pretty easily. So decreasing on 0 to infinity and increasing on minus infinity to 0. All right, and now intervals of concave up and concave down, and we're just going to differentiate again. So This is now the second order info. And we differentiate again. So it's a product rule. Differentiate the first guy, leave the second guy alone. Leave the first guy alone. Differentiate the second guy. Let's factor out a 2, and then we're going to have a positive positive, so we're going to have 2x squared. Let's factor out a 2 and an e to the minus x. E to the minus x squared. So e to the minus x squared, and from this thing we are going to have a 2x squared, positive sign, and then from this thing just a minus 1, because we've factored out the 2 already. Yeah, okay, looks good. So that's the second derivative. And this first part here is always positive, so the sign will just be determined by this thing, right? And let's further factor out a 2. And then let's break up this, because this is the difference of 2 squares, right? X squared minus a half, and a half is a quarter squared. So let's write that as 4 e to the minus x squared, x minus 1 over 4, x plus 1 over 4. And now we are happy, because we can create our table. So we are going to go from minus infinity to minus 1 over 4, minus 1 over 4, 1 over 4, 1 over 4 to infinity, and then we put in our factors, x minus 1 over 4, x plus 1 over 4, and then second derivative. And now we can figure this stuff out. So let's fill out the table. So when x is negative, this is for sure negative. We are still negative here, and we're positive here. Now here we are still going to be negative. Here we are now going to be positive, and here we're going to be positive. So we have positive, negative, positive. Cool. So we have here minus 1 over 4, 1 over 4, and we should be concave up, and concave down, then concave up again, and sure enough, that thing we can have, and it's consistent with what we know. Concave up, then concave down, and then concave up, like this. Yeah. And let's just further convince ourselves. Let's put some tangents underneath. This thing can, it's not a good picture. Do that again. Making a mess. I'm making a mess here. All right, forget about that side. Let's look at the other side. So we can put a tangent underneath this part, and that'll make sense. And then tangents will fit on top on this concave down part right here. And all that stuff is fine. So we have analyzed this guy completely. So local maxes and local mins, it only happens when the derivative changes sign. That's only going to happen at 0. So local max, because we we are positive to negative, right? So local max at x equals 0, and the local max is the value when we stuck it in. In this case, I can calculate it easily. The local max is, putting 0 into this function, where it is, there it is just equal to 1. We know it is c up on minus infinity to minus 1 over 4 and 1 over 4 to infinity, c down on minus 1 over 4 to 1 over 4. And points of inflection are where we go from being C up to C down or C down to C up, and that's going to happen here and here. So points of inflection at 1 over 4, and what will that be? That will be e to the minus 1 over 16 and minus 1 over 4 e to the minus 1 over 16. And that's it. That's everything we can know. All right, so these are not all the tricky questions, but these are amongst the ones I think are the harder ones. If you're serious about this exam, you will do the entire exam and know it really. You'll do the entire practice exam and know it very, very well. And you'll also do the 2 past exams. So you still have time. Please use that time. Please keep preparing, and good luck tomorrow.